Hello everyone from Math 2200, Discrete Mathematics. Professor Wenson here again with a video on your Zybooks section 11.2 titled Binomial Coefficients and Combinatorial Identities. Alright, so let's just get into it. Alright, so the first part of this section is on identities, which you've probably heard the word identity before. Back in, I'm sure you saw them in trigonometry class, right? Trigonometric identities. And combinatorial proofs. Now, whenever you hear the word combinatorics or combinatorial, it just means you're counting. Right? Just a lot, we've these past, chapter 10 and so far in chapter 11, right? This has been all about counting combinatorics. Right? So an identity is a theorem stating that two mathematical expressions are equal. An identity that involves expressions related to counting is called a combinatorial identity. Right, again, fancy way to say identity for counting. So here is an example of a simple combinatorial identity. And this is one you've already seen. N choose k is equivalent to n choose n minus k. Right. And they take you through a little bit of an algebraic proof here. An algebraic proof of this identity would involve showing that each of the expressions above is equivalent to, remember the formula for n choose k in terms of factorials was n factorial in the numerator divided by k factorial times n minus k factorial in the denominator. And you could very easily show that both of these are equivalent to this. Alternatively, the identity can be established using counting principles. Right? N choose k is the number of ways to select k items from a set of n items. However, instead of specifying a k subset by selecting the k items included in the subset, we could select the n minus k items excluded or not in the subset. And there are n choose n minus k ways to select those. So the number of ways to select k items to include is exactly the same as the number of ways to select, the n minus k items not to include. And again, you've seen an example of this. I'll do it with specific numbers here. 5 choose 2. This is like having 5 slots, and I choose where, and maybe I have 2 categories here, yeses and nos or something. And say I have 2 yeses, number of y's is 2, and say the number of no's is 3. One thing I could do is I choose where the yeses go. Maybe here and here, and then the n's will go everywhere else, right? Or here and here, here and here. 5 choose 2 is like choosing where the y's go. Well, instead of choosing where the y's go, I could have also just chosen where the n's go. Say choose these 3 spots for the n's to go, then the y's have to go here. So 5 choose 2 is the same as 5 choose, 5 minus 2 or 5 choose 3. And again, you've seen this, right? This identity has been shown to you before in chapter 10. A proof that makes use of counting principles, like they described in the previous paragraph, is called a combinatorial proof. Combinatorial proofs usually involve defining a set S and counting the number of elements in S to get a mathematical expression for the number of items in that set. Then the elements in set S are counted by an alternate method to get a different mathematical expression. So just like I did with the, where do I put the y's and n's? 5 choose 2 is how I count the number of ways to choose, put the y's down. That's equal to 5 choose 3, where I counted it a different way by counting the number of ways to put the n's down. Every combinatorial proof of an identity uses a bijection implicitly, as part of the argument. The reasoning can be checked by explicitly stating the bijection and verifying that a bijection has the required properties of a bijection, right? It's 1-to-1 and on to. In the example above, the bijection maps each K subset, the items chosen, to the complement of the K subset, right? The items not chosen. So the complement of a K subset chosen from the set of n items is an n minus k subset. Hence, there is a bijection between k subsets and n minus k subsets. And they illustrate this below. Right, I'll play the animation. So, wow, look at this. They're using basically 5 choose 2 and 5 choose 3. Alright. So look. Here's a set of 5 objects, red, blue, green, red, orange, and pink. So here they're counting the 2 subsets, the blue and green, and then they're saying there's a bijection. Let's have every 2 subset correspond to a 3 subset with the colors that aren't in the subset, right? So blue and green are in this, and then the red, orange, and pink form a 3 subset. And this continues for all the 2 subsets. Blue and red would then correspond to green, orange, pink, blue and orange to green, red, pink, and so on. And they do this for all 10 2 subsets. And if you do this, you'll see there's a bijection, a 1-to-1 correspondence between 2 subsets and 3 subsets. Therefore, the number of 2 subsets must be the same as the number of 3 subsets, when you have a set of 5 distinct objects. Therefore, 5 choose 2 must be equal to 5 choose 3. Right. Okay, and that's what they're explaining down here. Wonderful. Alright, so based on the identity above, which expression has the same value as 12 choose 4? Well, that would be 12 choose 8, wouldn't it? Okay. Furthermore topics. The binomial theorem presented below gives rise to other combinatorial identities. Alright, so the binomial theorem. Now you may have seen this before in some pre-calculus or algebra class. You may not have. I know some schools, it's not particularly a topic covered in an algebra 2 or a pre-calculus course. So you know what a binomial is, right? A binomial is just an expression with 2 terms, so like a plus b. The binomial theorem has something to do with raising binomials to whole number powers. So like a plus b, to the 3rd, like they're doing here. So if you look at this, now they wrote it in a kind of a weird way. Normally you just write this as a cubed, a plus b to the 3rd power is a cubed plus 3a squared b plus 3ab squared plus b cubed. They wrote this out as a times a for a cubed. Then there's aab, aba, and abb. Oh, sorry, they should have reordered this. aab, aba, and baa are all 3 of the a squared b's, 2 a's and 1 b. Then you have abb, bab, BBA, those are the 3 AB squareds, right, with 2 B's and 1 A. And then you have 1 BBB, 1 B cubed. So you see there is a term for every string in the set AB cubed, right, the Cartesian product of A and B with itself 3 times, right? So every string of length 3 with letters A and B in it are represented by the terms of A plus B cubed, this binomial cubed. And again, of course, since A and B commute, you can put these together like this. Right? So the coefficients in the above expression, the 3s and the 1s, the coefficients in that expression are called binomial coefficients. So 1, 3, 3, and 1 are the binomial coefficients here for this binomial cubed. For general powers n, right, raising a plus b to the nth power, the coefficients of the terms in a plus b cubed can be expressed using ideas from counting. Notice that before putting the like terms together, coalescing, right, before putting like terms together, there is a product of a's and b's for each possible string of length n, right, of length 3, over that alphabet a and b. So for example, if you raise to the 7th power, the term AAB, AAB, AB, AA is equivalent to a to the 5th b squared. And then you could ask, how many terms have a to the 5th b squared? Well, you would just count how many strings of length 7 have 5 a's and 2 b's. Right? So it's just these coefficients of a binomial expansion, right, a binomial raised to a power, are just combinations, just counting numbers. So the number of such terms is, again, the same as the number of strings of length 7 with 5 a's and 2 b's. So from counting arguments, the number of strings is 7 choose 2, or 7 choose 5. Remember, 7 choose 2 is the same as 7 choose 5. The binomial theorem says that the coefficient of a to the k times b to the n minus k in the expansion of a plus b to the nth power is n choose k, or n choose n minus k, because they're the same. Alright, so you get this crazy expression here. Now you've seen sums, right? We've talked about sums before. The binomial theorem states the following, that if you take a binomial, sum of two terms, a plus b to the nth, and n is a whole number power, you're getting a sum, the sum from k equals 0 to n, of n choose k times a to the n minus k times b to the k, or this is equivalent as well, n choose k times a to the k, b to the n minus k. So their first example here shows you, how you would write a plus b to the 5th out. And let me actually go over some of these. Let me write some of this stuff out. So let me start taking binomials to powers. So if I take a plus b and raise it to the 0 power, well, remember, anything to the 0 power is just 1. Right? Anything that's not 0 to the 0 power is just 1. And really, you can think of this as the number of strings of length 0 that you can form with letters A and B. And there's only one string of length 0, that's the empty string, so that's why this is 1. Okay. Then what about a plus b to the 1st? Well, this is just a plus b, isn't it? 1a plus 1b. 1a plus 1b. And again, if you think about it, there's only one string of length 1 that you can form with a and b, and there's only one string of length 1 that is just this a. That's it, the string a. And there's only one string with one b in it, the string b. And you could also think of these numbers as 1. You could say 1 choose 1 or 1 choose 0. Right? I have a string of, I'm making a string of length 1 and I choose none of them to be B's or one of them to be A's. And then this number, again, could be 1, choose 1 for the number of B's in it. You choose the number, choose where one. I'm making a string of length 1 and I choose where the 1B goes, or 1 choose 0. Okay. Next one, A plus B squared. So again, this is going to be like, hey, let's form strings of length 2 with A's and B's. Well, I could have two A's, so that'll correspond to A squared. I could have an A and a B, and that'll correspond to AB. Or I could have a B squared, BB, two B's, that corresponds to B squared. And then again, the coefficients of these are just how many strings like that can you form with the letter of length 2 with the letters A and B. So how many strings of length 2 can you form with two A's? Right, AA. Well, just one of them. Right, A and A, that's it. Plus, how many strings of length 2 can you form with A and B with one A and one B? Well, I can do A then B or B then A. So there are two strings like that. Plus, then how many strings of length 2 can I form with A and B where there are two B's, right? B squared here, BB. And that's it, just B and B. So just one. And again, the way you think, now let's just imagine, let's just say we're choosing the B's here. So this first number, the 1 on the A squared, you could think of as, I'm forming a string of length 2, and I choose no B's, right? 2 choose 0. This number for the next term, I could think I'm forming a string of length 2, and I choose 1B, 2 choose 1. And then this last term, I'm forming a string of length 2, and I choose both of them to be B, 2 choose 2. Okay. You see what's happening here? When I do a binomial expansion like this, I'll just start off with the first term to that power, and then every term after that, I just decrease the power by 1. So you see A squared, A to the first, A to the 0. And then start off with none of the second term, none of the B's, and then increase that power by 1. So you see B to the 0, B to the first, B to the second. And then all the coefficients are, again, just how many strings of this length, whatever the power is, can you form with that combination of letters. Now, they already showed you, right? They already showed, oh, you know what? I'll just do it. I don't know why I did that. All right, I'll just do A plus B cubed. Right. So sorry about the dot, dot, dot there. So again, I can have 3 A's, and then just decrease the power of A by 1. I can have 2 A's and a B, or 1 A and 2 B's, AB squared, or all 3 B's. I'm imagining forming strings of length 3. And there's one of these, right? They said plus, and there are 3 of these strings, with 2 A's and a B. There's AAB, ABA, BAA, right? Plus there are 3 strings with 1 A and 2 B's, and there's only 1 string with 3 B's. And again, all these numbers are just combination, just choosing numbers. This is 3 choose 0. This coefficient is 3 choose 1. This coefficient is 3 choose 2. This coefficient is 3 choose 3. All right, and so on. Now, you could continue doing this, but it gets a bit hairy after a while. You notice how every single time there's one more term, the polynomials are getting longer. So now what if they asked us this? They have an example here where they say, hey, well, look at, how about this binomial? Instead of A, well, it's 2A. And instead of plus B, they got minus 3B. but it's still a binomial, right? There are still two terms, 2a and negative 3b, right? The b here is replaced by negative 3b. And say I raise this to the 6th power. Now, I could easily expand this, right? But what they ask, what they might ask you is, what is the coefficient? The numerical part. They might ask, what is the coefficient of the a squared b to the 4th term? Right. Now you can do this in one of two ways. One way is you can just expand it all out and look at the a squared b to the 4th term. Another way is, look at just one term. Look at the term that would have a squared and b to the 4th in it. Now you gotta be careful, right? This is my first term. This is like the a from earlier, what I'm putting in a blue box here. And then this negative, remember negatives are part of the terms, right? This is plus negative 3b. This is the second term. So the a that I originally had is now replaced by 2a. And the b that I originally had is now replaced by negative 3b. So I'm going to first look at, what would be the expression here? I'd have the blue box squared, 2 of the blue box, 2 of these 2a's, and then I need 4, for b to the 4th, I'd need, this negative 3b to the 4th. Right, so we're looking at the 2a squared times negative 3b to the 4th. And then what would be the coefficient in front? What would be the combination number? Because remember, all these I'm forming a string of length 6. So I'm forming a string of length 6. Right, that's the power. And I choose 2 of them to be the blue box or 4 of them to be the red box. So the coefficient here is 6 choose 2 or 6 choose 4. And then I'm going to multiply this out and get the number that's in front of a squared b to the 4th. Okay, so again, this is in parentheses 2a to the 2nd, in parentheses negative 3b to the 4th, right? The first term to the second term to the 4th. Now, 6 choose 2, that'd be 15 times, and then 2a to the 2nd would be, 2 squared a squared. And then negative 3b to the 4th would be, negative 3 to the 4th b to the 4th. All right, so the coefficient here is going to be 15 times, 2 squared is 4, times, and then the only thing with a number in it is negative 3 to the 4th is 81, and then you have a squared b to the 4th. All right, multiplying these out, and I'll pull up a calculator here and go 15. Well, I should have said 60. Well, actually, that's 4880, isn't it? 15 times 4. Oops, I put double times. 4 times 81. 4860. Whatever. So 4,860 times a squared b to the 4th. And that's what they're talking about. There's the coefficient that they're looking for. Right? The coefficient of a squared b to the 4th. All right. But to see what happened, though, right? Again, instead of just a and b, they were replaced. Right, and if you want, you could replace them. I could say, let's call the 2a capital X and the negative 3b capital Y, and then I'd have a bunch of terms, and then get down to where I have x squared y to the 4th, and then the coefficient on that would be 6 choose 2 or 6 choose 4, and then then I have exactly what I had here when I did the blue box, red box stuff. Okay. All right. So hopefully that made sense. I'll probably do another one of these in a second. So you see they're running through that here. And then if you take a look at the, if you use this binomial theorem, you can set up all sorts of identities. Like 2 to the nth power is the sum of all the combinations from n choose 0 up to n choose n. So the sum of all these, 5 choose 0 plus 5 choose 1 plus 5 choose 2 plus 5 choose 3 plus 5 choose 4 plus 5 choose 5, the sum of all those would be 2 to the 5th. That would be 32. And hopefully you can see where this is coming from. All I would need to do is replace, in my binomial theorem, replace a and b with 1. Right? 1 plus 1 would be 2 to the nth on the left here. And then 1 to any power is 1. So those disappear, and then you just have the sum of the combination numbers, the sum of the n choose k's. And that's exactly what they do in the animation down here. Right. Here's another identity from the binomial theorem. So this is saying if you alternate the sum, if you take positive n choose 0 and then minus n choose 1 plus n choose 2 minus n choose 3 plus n choose 4 minus n choose 5, etc., all the way up to whatever you're either adding or subtracting n choose n, that's going to be 0. It's going to be 0. Again, a way to see this would be to replace a with 1, replace b with -1, and that formula will come up. This will come up. All right. Okay. All right. So let me do another one, like I said, like I did earlier with the binomial coefficients. So what is the coefficient of x to the 4th y cubed in this binomial to the 7th power, 3x minus y to the 7th power? Okay, so here it is, 3x minus y to the 7th power. Like I said, it's a binomial, so what are these terms? Well, one of them is 3x, and the other one is negative y. Don't forget, subtracting is just adding the opposite. So it's 3x plus negative y. Now, if you'd like, you could call the 3x a and call this negative y b, and then all of a sudden you have a plus b to the 7th and expand this. But then just replace the a and b with 3x and negative y when you're done. Now they asked us for the coefficient of the x to the 4th y to the 3rd term. So in order to get x to the 4th, I would need this first term to the 4th power, wouldn't I, to get x to the 4th. So I'd have, this is equal to something, 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 and then, plus, and then I'd have a to the 4th, right, the 3x to the 4th. And then, to get the y to the 3rd, if I have 4, if I'm creating strings of length 7 here. If I have 4 of these a's, I would have to have 3 of the b's. And then remember, the coefficient on this is 7 choose 4 or 7 choose 3. Right? A string of length 7, choose 4 a's or choose 3 b's. Okay, so now I just go back and replace. What is a? A was the 3x. So this is 7 choose 3, 7 choose 4, doesn't matter. Times a is 3x to the 4th times b is negative y to the 3rd. And then we'll multiply stuff. Now 7 choose 3 would be 35. And you can find that in the calculator or whatever. I just know these pretty well. And then times, and then 3 to the fourth times x to the fourth, right? 3 to the fourth times x to the fourth. Times, and then -1, right, the coefficient to the third, times y to the third. And then what we got here is 35 times, 3 to the fourth is 81. And then times, -1 to the third is -1. And then you have your x to the fourth. I'm just rearranging the factors here. So we got our x to the fourth, y to the third. All right, so here's the coefficient. All right. And 35, I don't have to pull the calculator up for you. I'll just do it off screen. 35 times 81, you hear me clicking. So this is negative 2,835 x to the fourth y cubed, right? But what they want is the coefficient, right? Back here. Oh, I should have looked at the choices. Yeah, it was just this 7 choose 3 times, the opposite of 81, -81. This one here. Yeah, but that's negative 2,835. Okay. All right, and then I use the binomial theorem to give an expression for this guy. So back up here, they give you the sum, so this side. Basically, what's the a and the b? What do they replace a with and b with to get this? So it looks like you have, the 2 and the x are both to the 10 minus k. So 2x is one term. And then you see -3 and y are both to the k, so -3y is the other term. So this would be 2x minus 3y to the 10th, right? Because all these are 10 choose, 10 choose, 10 choose, so you're raising the 10th power. It'd be this one here. Okay. All right. Next is Pascal's triangle. Now, I had a page up a second ago where I started raising these raising binomials to whole number powers, starting with 0. Let me show you that again. So that was this. Now, do you see the triangle shape? Starting off at a peak up here and then expanding out. Now, what if I were to just write the coefficients, right? Instead of using the letters, I'm just going to write this same thing, but with the coefficients. So you can probably still faintly see them. When I did a plus, we'll call this the 0th row, because I was, that was when I raised a plus b to the 0, right? And then the next one we'll call the first row, because it's when I was raising a plus b to the first, and I got coefficients of 1 and 1, which were 1 choose 0 and 1 choose 1. Then when I raised a plus b to the second, we'll call this the second row of the triangle. I had 1, 2, 1. And then finally I'll do the third row here. When I raised a plus b, when I raised the binomial to the third power, we had coefficients of 1, 3, 3, and 1. Right. Again, this was 0. You could call this 0 choose 0. These were 1 choose 0, 1 choose 1. The second row numbers were 2 choose 0, 2 choose 1, 2 choose 2. And the third row numbers are 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So that's why I named these rows the way they did. Again, these rows correspond to the powers that I was raising the binomial to as well, these row numbers. And what you're seeing is that, getting all the combination numbers. Now I'm going to put out one more row and show you a pattern. So here's the fourth row. So these would be the coefficients if I were to raise a plus b, a binomial, to the fourth power. So 4 choose 0, which is 1. Anything, any whole number choose 0 is 1. Then between these two, I'm going to put 4, choose 1, which is 4. Between these two, I'm going to put 4, choose 2, which is 6. Between these two, I'm going to put 4, choose 3, which is 4. And then finally, again, this should be expanding, but I'm running out of paper here. 4, choose 4, which is 1. There's a nice pattern going on here in the formation of this triangle. Well, first of all, you got 1s down this side of the triangle and 1s down this side of the triangle. And then in between, if you go from one row to the next, you take any two consecutive numbers in a row and add them up. You're getting the row in the row. You're getting the number in the row below it. All right. See, 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And so, keeping up with this pattern, I can tell you also now all the coefficients in the 5th row. So again, start with 1, and then 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and then you got 1 again. Sorry, again, this should be expanding, but again, I'm out of paper. So these would be the coefficients if I were to expand, a plus b to the 5th power. All right, so what's going on here? So I'm going to write some things down. So what we see, again, what was I saying there? What was this pattern? So just for some examples here, we had, 2 choose 0 plus 2 choose 1 was equal to 3 choose 1. All right. We see here, I'll just pick another one. 3 choose 1 plus 3 choose 2 was equal to 4 choose 2. And again, if you go down a little diagonal, these are all the choose 0 numbers. These are all the choose 1 numbers. These are all the choose 2, choose 3, choose 4, and so on. Right? Choose 4, sorry. So what I'm noticing here is that if I'm in row n, right, if I'm in row n, if I do, say, n choose k, and then add to it the next one over, which would be n choose k plus 1, I'm getting a number in the next row, the n plus first row. So n plus 1 choose, and then the same, I'm in the same diagonal, so I'm choosing the same amount as this second number here, k plus 1. And this is called Pascal's identity. Now, I haven't proven it. All right, I've just showed you a couple examples. This is not a proof. But you could very easily show, you could show algebraically, just show do the formulas for these and show that when you add them up, you get the same as the formula for this. It'd be very easy to show algebraically. And then they also go into a combinatoric proof for Pascal's identity. So they run through here, blah, blah, blah. All right, so they used n minus 1 and n. I used n and n plus 1. But if you're in one row and add 2 consecutive numbers, you get a number in the next row, right? Choosing the same amount as the second number up here. So it has n minus 1 choose k, and then down here it's n choose k. They're both choose k. So here's Pascal's identity. All right, so they show you here a combinatorial proof of Pascal's identity is shown below. But first, the following animation. All right, so they just basically show you what I wrote on paper. All right, and you can read through this if you wish. This is just using counting principles. So they're gonna describe to you how if I have n objects and I count the number of k subsets, That'll be equivalent to if I take n minus 1 objects, count the number of k minus 1 subsets, and then add to that n minus 1 objects, count the number of k subsets, and they go through a combinatorial proof of that statement. All right, so here is the 6th row. All right, so this is 6 choose 0, 6 choose 1, 6 choose 2, 3, 4, 5, and 6. All right. What would be 7 choose 4? So remember, in order to find 7 choose 4, I need 6 choose 4 plus the one before it, 6 choose 3. So 6 choose, again, 0, 1, 2, 3, 4, these two numbers. 6 choose 3 is 20, 6 choose 4 is 15, 20 plus 15 would be 7 choose 4, would be 35. And then what's 7 choose 5, right? Again, now this is using the pattern using Pascal's identity. Now I know you could find these without the identity, right? You know the formula is for combinations. But if I want 7 choose 5, I need 6 choose 5, and then plus the one before it, 6 choose 4. So 6 choose 5 is 6, 6 choose 4 is 15, add those up, you'll get 7 choose 5, which is 21. Great. All right, and then again you have your addition. Now you have your additional exercises. Not too many of them. I think I might have assigned all of these actually. Maybe not the proofs, I don't know. But even if they aren't all assigned, I would still recommend looking at all of them. All right, get more exposure to the material, more practice. And you got also the solutions to look at if you need to, right? Just to check yourself. Don't rely on those though, right? Don't try to work them out first. Try to figure things out before you look at the solutions, because you're not going to learn anything if you're just copying solutions down and not trying. And hopefully this video is a good guide for this section. If you have any questions, of course, send me a message and I'll get back to you as soon as I can, as soon as possible. And thank you very much for watching.